Hey folks, in this video we're talking about phase changes. What? Yeah, well I want you to be able to explain how physical processes or physical reactions, it's not as good a word, are different from chemical reactions. I want you to be able to define phase changes, the titular words of this video, and I want you to be able to calculate the energy that's absorbed or released during a phase change. All right, cool. Well, let's talk physical versus chemical. In a physical change, no chemical bonds are altered. This is really important for distinguishing these two things. When you boil water, when you're boiling things, that's liquid water becoming gaseous water. There's no bonds that are actually being broken in the molecules that make up that water. They're just moving around differently. The same thing is true for like anytime something melts or becomes a solid. If a liquid becomes a solid or a solid becomes a liquid, that does not mean a chemical reaction has taken place. It's more likely that just a temperature change really has gone down. A solid water and liquid water are both water when you melt ice. That's not a chemical reaction. It's a physical change. Now, this is a good example here. We've got our solid water. It's all nicely arranged. This is what ice is, but the same molecules make up liquid water. This beautiful stuff here that I'm going to take a sip of, they're exactly the same. Same thing is true for dissolving. Some people think that a chemical reaction takes place when salt dissolves or sugar dissolves, but that is just another phase change. That is simply a solid dissolving and breaking apart. Here we can see a sugar crystal is lots of sugar molecules together, but when they dissolve, they simply break apart from each other and move about inside of the water. Yummy water. So, what's a chemical change then? In a chemical chain, bonds are actually broken or formed. Like these pretty little connected guys, they might get broke. An example here is if we have hydrogen and oxygen that react together to form water, there are bonds that are broken. These hydrogens are bonded together, and then those bonds are ripped apart, and they're now bonded to oxygen, which used to be attached to each other. So things that are broken apart. The actual bonds that hold these things together are changed and rearranged. Well, let's talk about phase changes, because a phase change is related to the different phases of matter. When we have a phase change, we're changing between phases of matter. And so these would be common ones that are solid, liquid, and gas. There's other fancy guys like plasma and Bose-Einstein condensate and other weird things that scientists are discovering. But we're going to focus on solid, liquid, gas. These are the common ones that you will encounter just walking around in life. Well, phase changes when matter, as I said, changes between these phases. So if a solid becomes a liquid, melting, that's a phase change. If liquid boils to form a gas, that's a phase change. So these can be caused by either temperature changes or pressure changes. You know, if you squeeze on most substances with high enough pressure, they will form a solid. Water's different, and that makes water a badass. We're going to focus on temperature changes and not pressure changes so much. And so we can calculate the amount of heat that's absorbed or lost during a phase change. For this, we're going to have a fun delta H. We've mentioned these in previous video, heat of fusion and heat of vaporization. These are terms that we're going to use, but we're generally going to use them, what kind of phase change described here, in an equation Q equals our phase change times the mass. Really nice and easy. So if we're melting or freezing something, we're going to use the term delta H of fusion, the enthalpy of fusion. And so this is interesting because the amount of heat that is absorbed when you melt something is going to be the exact same amount of heat that is released when that thing freezes, if you cause it to freeze. So melting and freezing connected in the amount of energy that's required. Same number. And so if we're boiling something, turning it into a gas, or condensing it, we're going to use the enthalpy of vaporization. And just like here, you know, if you have 100 grams of water and you cause it to vaporize, it's going to vaporization. Well, that's going to, of course, absorb heat. And if it then condenses, it's going to release that exact same amount of heat back out. We can also use the molar enthalpy of vaporization and fusion, kind of like we can also use molar specific heat instead of a molar heat capacity. Neat stuff. And so these are then going to have units if we talk about the molar enthalpy of joules per mole or kilojoules per mole. You're killing me, little slide thing. I don't know how to disable you. It makes me feel like such a noob. Anyway, more on phase changes. So in order for a phase change to occur, this is kind of important. The entire sample must be at this transition temperature. This is the temperature at which a phase change will occur. So we would usually call this boiling point or freezing point. Melting point would be the same as the freezing point. And this is going to be dependent on temperature. You may have heard that if you want to boil something in Colorado up in the mountains, that it will take more time. That's true because water boils at a lower temperature at that low pressure. And so it doesn't take as long to boil water, rather, but your water won't cook things as fast because it doesn't get as hot. It starts boiling at a lower temperature. Anyway, boiling point. This is the temperature we'll transition between liquid and gas. And then we also have our friend freezing point, which we will transition between liquid and solid. You could also call this the melting point or the condensation point. But we're going to call them boiling and freezing. So this is true for an idealized mixture, but this is definitely not true for real life. Like if you have an icy drink and you're not mixing that up, you might find that it's kind of warmer at the bottom than around those ice cubes. Or if you think about the ocean, there's definitely ice floating around the ocean, although less and less every day. And there's also warm spots in the ocean, like on some nice tropical beaches. So yeah. The ocean is not a super idealized mixture, but if you did perfectly mix the whole thing up, it would come to one nice temperature. Cool. So during a phase change, yeah, we're going to have a mixture of our two different states, and that's kind of fun. So if you have ice water, perfectly mixed up ice and water mixed together, there's both liquid and solid there. That should be at the freezing point. So if you have a perfectly mixed sample of water, it should be right around 0 degrees Celsius. Yeah, and until the rest of that water freezes or the rest of that ice melts, the temperature should stay there if it's being perfectly mixed. That's kind of cool and important for a thing we're going to talk about in the next video. But let's do some practice with this Q equals delta H of vaporization or fusion times mass. So we got 100 water. Yeah, it's at 100 degrees Celsius, and it suddenly vaporizes and absorbs 56 kilojoules of heat. What's the mass of that sample? We got some information. Pause the video. Give it a shot. It's not fast place. All right, you pause the video, give it a shot. Well, we're going to use our Q equals delta H of vaporization times the mass of that water. And what do we know? Well, we know this guy, and we don't know the mass of the water, but we do know Q. So let's plug what we do know in. And we're probably, since this guy's in joules and this guy's in kilojoules, we're going to need to use this. So if we got 56 kilojoules, that's 56,000 joules. Neat stuff. We can plug this into our equation now. All right, the only thing we don't know is mass. We can just divide both sides by 2257, and that's going to give us our mass of the water. Not too spicy. Let's try one more. More practice, my people. Give it a shot. All right, cool. Let's go through this together now. We got 490 grams of liquid water. It's at 0 degrees Celsius, and it suddenly freezes. How much heat is it going to either absorb or release? And we know our heat of fusion is this guy. Okay, cool. So this is in kilojoules per mole. So if we're going to plug into our Q friend, we're going to need to know moles because, yeah, we need moles to interact with this properly. And we don't have moles right now. We just have grams. So we need to know the moles of water if we're going to do this properly. Well, we're going to have to use our molar mass of water and use that to convert from our grams into moles. So we'll set up our sweet X line action and solve for the number of moles of water. Okay, cool. Well, now we can plug this 27.2 moles of H2O into this guy. These moles will multiply with those moles to cancel out. Very, very nice. We'll get a Q value of 164, and we'll be like, great, done. Are we done though? Is that number correct? Let's think about that. Is 164 kilojoules for Q correct? Well, we said that if it's freezing, it's going to release heat because the particles are moving less. So if we're releasing 164 kilojoules of energy, that should be a negative Q value. Q is negative when we are releasing heat. Yeah, this dude is releasing heat, and therefore it has to have a negative Q value. Sneaky wine grad. You are a sneaky boy. Anyway, that's the end of this video. Yeah, ta-ta. Have a great rest of your life.